Now, going on to topic 3 of chapter 4, modeling with exponential functions. Now, here we're looking at how exponents can really magnify the calculations that are going on here. So let's read this carefully. Growing linearly, the balance owned on your credit card triples from this to this in 9 months. Wow. If the balance were growing according to exponential function, though, what would it be if we use this function? Let's just write it out here. 500. Now, notice it's 1 plus this 13% here. So we can join that together as 1.13. And then the exponent here is going to be a 9 because the x is the number of months. Now you're going to need a calculator to do this. So let's pause and see what you get. So this one's not too bad. It's only increased by $2 more than this. But notice, boy, that is really a stinging thing. If they're charging 13% interest per month. Wow. Okay, let's go on to number 2. We're going to read it carefully and see if you can now substitute into what's there, and then we'll pick it up from that point. So this would be the function, and again you can join these two together, and then it's to the 12th power. Again, you want to see if you're using your calculator correctly. So again, in the linear function it was 2100, in the exponential function it's a little bit more. But notice, and I should have mentioned this earlier, that they're asking us to round to the nearest cent. So we would go to the third decimal place. That's a 9. So we're going to drop all this and make this 2 here a 3. That would be the answer. Now, if you put a 2 there, the software is going to count that incorrect. So be careful about rounding off. All right, let's go on. For number 3, we'll let you read it over. And again, you want to set up over here what the function would be. But notice now our exponent is so much larger. It's going to be 40.5. Now notice, if it were linear, it would end up being this, but exponentially, check this out. Now take a look at this. So in 40.5 months, linear progression, you'd go from 600 to 6,000. But exponentially, instead of 6,000, this is 84,000. Wow. And again, you're going to round off to the nearest cent. So you go to the third digit, which is a 5, you drop that, and this 3 will become a 4. Wow. Can you imagine? Exponential growth. And in our flipped classroom lesson, you recall the king who was going to give 5,000 or 50,000 each day, and compare that to adding just 2 cents. that was going to be developed exponentially. Again, in the beginning, it doesn't go up that fast, but again, as you add time, that curve shoots up like a rocket ship. Wow. Exponential growth. All right, looking at example 4, take a moment to read it. And for background information, continuous interest formula is A equals principal times E, which is Euler's E, exponent rate times time. So let's see if you can set this one up. All right, principal is 7175. Euler's E on our calculator. And the investment rate is exponent 0.08. And it's 13 years. So times 13. And I'd put that in a calculator. So you could put the whole thing in. Another way is you put E, caret, and then some calculators has the caret built in. So you have to be familiar with your instrument. And then let's see what you get. So again, 8% is a pretty good interest rate. We don't get that much anymore. But compounded continuously, your future amount after 13 years is $20,299, and they're asking us to round to 2 decimal places, or the nearest cent. Our third decimal place is a 2, so we're going to drop that, and then this is our answer. All right, moving on to example 5, it's similar. Here it's 5%. Again, continuous interest. A equals P, Euler's E, RT. All right, take a moment, set it up, see what you get. So 8650E, caret, put that in parentheses, 0.05, converting 5% to its decimal form, times 22. And let's see what you get for an answer. So from 8,650 after 22 years, 5% is not that much, but again, that's still very good in these times. You end up with 25,986. You're rounding off to 2 decimal places, so you look at the third decimal place, it's 6, so it's going to drop this and make that 3 a 4. Again, the software is very critical about rounding. All right, one more to go. Now, in summary of what we've been doing as we look at this, we are wondering, I'm not sure why I'm getting such a thick pen here. Let's try it again. There, that's better. Whether our growth is linear or whether our growth is exponential. So linear is a straight line, exponential is a curved line. So here we have the number of bacteria in a test tube is increasing by 4 bacteria every second. And we want to say what function models this situation. So take a moment, reflect on it, and we'll see what you get. Well, it's this first one right here. So 4 bacteria for every second. Now you're starting with 1, and then X is your seconds, and that's the type. Now notice this is going to be linear growth. All right, we'll wrap this up. Any questions as we move on to our next topic in Chapter 4? Again, hopefully you're keeping up with your quizzes and your practice and certify. And of course, if you have a question, be sure you're asking it. And again, on Wednesdays, we do a notebook check.